Okay. Last time in class we talked about product rule a little bit, and this time we're going to talk about quotient rule. I'm going to show you today why it was that I wrote the product rule differently than the book did. The quotient rule says if I have an f of x equals a u of x over a v of x. Now, I realize that in here we've been leaving off the notation and we've said, okay, that's the same thing as a u divided by a v. And so I'm going to, again, leave off that notation, but understand that it means a function of x, we're calling it u, and a function of x, we're calling it v in the numerator and denominator. So when it comes to the derivative using this quotient rule, we end up taking the derivative of u times the v denominator function, and then we subtract the u times the derivative of v, and we divide that by the v function, not zero power, squared. And again, you'll find that in the front cover of your book, but you're going to find that this happens. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. And again, because it's product here, we can swap that order. If you want v prime times u, that's okay. If you want to write it that way, that's the same thing, it's a product. So that order can be swapped. But I'm hoping this reminds you somewhat of the same types of things that we did with product rule, where it was, I wrote down u prime v plus v prime u, or u v prime. You just swap the sign out, make it minus instead of plus. The book does it reversed, and it then I think provides a little confusion when you get to here. You start doing them in the wrong order. So that's why I did it the way I did. You see both similarities and, more importantly, differences between the quotient rule and the product rule. Okay, this is your time to be nodding your heads around?
Yeah.
Because I'm not seeing a lot of head movement. Okay, some of you are going yes. The next thing we really want to do is we actually want to use it. I'm going to take an example of it. So suppose I have f of x equals 6x minus 3 over 2x plus 5. And I want to take the derivative of this function. Now I hope you recognize that unlike some before, we had fractions, we had a single term at the bottom, and we could divide that single term into the numerator, and we got something we use a power rule on. This one obviously doesn't do that. It's totally different. So now we need to use this formula, and so what do I need to identify?
U prime and v prime.
Okay, so what's my u?
Equals 6.
What's my v?
2.
Okay. Again, early on, I want you to identify those, whether it be just like this or off to the side. But also off to the side, I need you to tell me what is u prime. Ooh, I heard that from somebody. Okay. And what is v prime? There it goes. Okay. Now we want to take a minute and try to put these pieces together using our formula, using our u v and u prime v prime. Okay, this is your chance to write something down. Some of you are staring at me. Some of you are not. This is your chance to write something down. I'll write something down here in a second.
Okay, I see what's happening.
Okay. Now again, some of you are saying, wait a minute, can I write it like that? Of course you can.
I was going to say, should we distribute it?
We will, yes. In this case, we actually will distribute.
Do we leave it? You want us to leave the denominator?
And that's the other good point. Yes, leave this as just the quantity squared. Do not multiply out the denominator. There's a couple of reasons for that. We'll talk about that in a little bit. But probably 99% of the time, we will not multiply that out. Because there's things that we do mathematically later, after we learn more about derivatives, that we will really want to leave that in the factored form. We also might discover that when we work our numerator out, that there's a factor up here that matches our denominator, and so we want to be able to cancel quickly. So please do not multiply out the denominator. It's a highly unusual case, if you will. Otherwise, are there any questions about this thing? Does it give you right here what you expected it to give you once we saw the rule? Okay, I'm hoping that part makes sense. Now let's multiply it out and see what we get as a result. 12x plus 30 minus 12x plus 6 all over 2x plus 5, the quantity squared.
Yeah.
Excellent. And a lot of times with these binomials like that, the x term will cancel out. Not every time, but a lot of the time. Especially if you've got x to the first in both of them. So f prime of x is going to be
30.
Yeah, 36 over 2x plus 5, the quantity squared. That's not too bad, is it? Any questions about that?
Is that just the answer?
Yeah, that's it. Okay? Well, yeah, what was the other title piece that I had for this thing? Not just quotient rule, not just product rule a couple days ago? And the other trig derivatives. Okay, guess what? Just decided to do some of them too.
So is that all in quotient wages?
That's it. I mean, that's what the quotient rule is. It's just that u prime v minus v prime u over v squared. If you can put those pieces together and identify u and v, it's just pretty straightforward in terms of applying it. A whole lot better than doing limits with all that, isn't it? Okay. Well, now suppose that g of x, actually, you know what? I need to do this. Suppose that y is equal to the tangent of x. And one of the things, I showed it on Melwork real quickly, but I really haven't talked about these derivative notation pieces very much, and I need to really visit about that briefly. We've used f prime, g prime, h prime. We've gotten used to that prime mark. When I write it as y equals, I have the option of writing it as y prime. We can do that as a notation. That means the derivative of y. Others of you saw me on the Melwork, and I wrote dy over dx, derivative of y with respect to x. That's another notation that means derivative, first derivative. That equals y prime. Then we're going to find out what that's going to equal in a minute. So I may use these interchangeably, and I will from time to time, but they mean the same thing. And so notationally, we need to, just be wary and be aware that those things happen. Bring that down there. The reason that I saved the tangent function until now is from our trigonometry, we remember the tangent is the quotient of what? Two trig functions. All that time last year was worth it. Right? Yeah, we'll find out, won't we? Okay, what's our first step? Okay. So, what's the u?
Sin x.
Therefore, u prime is... And also, what's the v?
Negative.
Not yet.
I jumped the gun.
Yeah, let's see it now. What's the v prime now?
Negative.
Thank you. Okay. So, we know from our derivative that it's going to be u prime cosine of x times v, it's cosine of x, minus v prime, so negative sine of x, times u sine of x, all divided by what? b squared, which is cosine squared of x. Do we agree that that is the correct first step in representing the derivative of the tangent function?
Yes.
Yeah. Okay. Now, if I collect cosine x times cosine x, what do I get? And minus a negative sine x is?
Plus sine squared x.
Guys, I think that looks pretty familiar to me. You think it's what? You think it's 1? Pythagorean identity? Do we agree?
Yeah.
Do you agree that's 1? So 1 over cosine squared of x? What's 1 divided by the cosine of x? What was that one?
Oh gosh.
That's secant. So secant squared x.
So we should be able to conclude that if y equals the tangent of x, then y prime is automatically the secant squared of x. And we won't go through the proof anymore. We'll just write down the answer. And you kind of see why it helps to have the proof a little bit to say, yeah, okay, now I really do see those two pieces fit together. Because without the proof, if I told you it was just secant squared of x, you're going, why? What happens? Does that make a little bit of sense, everybody? Okay.